This conference will now be recorded.
Okay, so now just I discuss the concept of the scaling. So scaling is a technique to reduce the transistor dimension. Okay, so how it is possible? We also discuss this concept on sometimes, but here you see what are the problems are facing nowadays in the VLSI domain. So if you talk about the processor, so there is some advancement of the processor i3, i5, and i7. So if you move to the higher order processor, the density of the chip is increased. That means the number of transistors, if you talk about the transistors, is increased in the particular area. Okay, I have taken one example here. Suppose that this is a chip, and here the area of this particular chip is 3 multiplied 2.5. So this area is fixed. But now if you go for the higher density of the circuit design, suppose that my density, so what the density means in a small area your number of transistors is more. So in that case, if the transistor is more, suppose that your density of the chip is very high, that means the number of transistor is also very high. Here the transistor is also transistor. If you talk about the number of transistors, that is very high. So if the transistor number of transistor is high, that means it is not possible in any way. You have to consume all the transistors in this particular area. This is not possible because the area is already fixed, but number of transistor is increased. So that is a problem are facing by many engineer or real estate industry in all the way. That is a problem we are facing this problem. So here how to tackle this problem and how to rectify this problem, because in the small area you fabricate more transistors, but area is already fixed. You do not increase more number of area. So in this way there is a technique. That technique is known as a scaling technique. Using this technique, okay, so this is a scaling technique. It is a very popular technique, and this is a very simple technique, but it is very fairly, this technique is fairly helpful to reduce the transistor size. So using this technique you have to reduce the transistor size. So if the transistor size is very small, in maybe your nano dimension, then it is a possibility you fabricate more number of transistor in this chip. So in this chip the area is already fixed. So if you reduce the transistor size, then it is a possibility to fabricate more number of transistor in the chip. So that is a way. You just remember this one. If the area is fixed, then you have to use this technique. That technique is a scaling technique, and accordingly your high density or high density chip fabrication is possible. So that is the concept, or that is a motivation of the scaling technique. Okay, so here the fabrication is very important. I already tell you the fabrication is your top level module, or maybe say that this is an end module or a end product. So in the end product, if you fabricate in a more number of transistor in a small area, then your area is then your that means you have to go for the high density chip design. So that is a frame or that is an overview of the scaling technique. So the one question, a very important question is why number of transistors is increased in a particular area? What is the requirement here? The requirement here, actually, if you talk about the processor, like your i3 processor or i4 processor or i7 processor. So if we move to the higher level of processor, of course the complexity, if we talk about the complexity is high. The complexity is more in case of i7 processor. The number of transistors is more in case of i7 processor as compared to i4 processor. And similarly, the i4 processor has more complex as compared to the i3 processor. So the main problem is the complexity, because here if the complexity is more, then of course your number of transistor is more in your chip. So you just observe here in this all the scenario, if you are moving from the from one processor to the top level processor or higher level processor, that is a complexity is a problem. The number of transistors is more in the higher order processor. So if the transistor is more but the area is not increased, so this is a one way how to tackle this problem. That the solution of this problem is number of transistor size must be less. Suppose that this is your transistor, maybe your NMOS or PMOS. So here the every transistor has a certain dimension. So suppose that this transistor area is W into L, but if you reduce the transistor size, if you reduce the transistor size, your W must be less and L is also must be less. If both value is less, suppose that you have to reduce the W. W is the width of the transistor and L is the channel length of your transistor. So if these two parameter is less, of course your area is also less. So your total area, if you talk about the total area of the transistor is less, that means your device is on the miniaturization stage. So that is a very beautiful concept here in this here the beautiful concept in that how to reduce the area. That is the problem, how to reduce the area, because here the two parameter is important, your W and L. Okay, so I think you understand the complexity of the circuit is increased day by day, and here the Moore law is also satisfied our chip. What is the Moore law? The number of transistors are doubled in every 2 years. So of course the complexity is high for every number, for every processor. Whatever your processor is moving from the higher level, the complexity of circuit is high, and of course the area is a very very means critical problem. This is a critical problem. How if you do not increase the area but you fabricate more number of transistors in the area, so that is only one possibility, you reduce the transistor size. So today I will discuss how to reduce the transistor size based on some technology, based on some terminology. That terminology is a scaling technology. Okay, so fine. I think you understand what is the concept of the scaling in the VLSI domain. Okay, so we will scaling in the VLSI. Okay, so today we talk about the scaling technique, how to reduce the transistor size. Okay, so here we are reducing the transistor in both horizontal and vertical dimension. Okay, in the horizontal and vertical dimension, both we are moving to reduce the dimension. Not only on the horizontal, we also work on the vertical direction. So if you work on the horizontal and vertical dimension, then your effective W and L ratio is reduced. That is our target point. Our target point is reduce the W and L. So we are talking about the reduction. If you reduce the value W and L, of course your transistor is on the nano scale or a small size. So that is our requirement. Okay, so that is only possible. The reduction of the dimension is only possible by the technique that is a scaling technique. Okay, so the reduction of the dimension both on the horizontal and vertical dimension is possible only by the scaling technique. Okay, so this is the overview. Okay, so now just one more discussion about uh, here. Suppose that uh, actually in the evolution of the VLSI, if we talk about the evolution or we talk about the advancement in the VLSI circuits, so here the main thing is that here the technology is available. Suppose that 180 nanometer. So what is the meaning here? What is the meaning of 1 nanometer, 180 nanometer? Your effective channel length, your effective channel length is 180 nanometer. So that means the channel is already fixed. The dimension of the device is already fixed. So the dimension of the channel, okay, just I talk about what is the channel, where is the channel. Okay, suppose this is your MOS transistor, and here some diffusion oxide layer, SiO2 layer, and in the top layer, this is a metal layer. So this is a metal oxide, and this is a semiconductor. So here in between the source and drain, and this one more terminal, this is a gate. So in between the source and drain, there is a part. This part is known as a channel, and this channel is length of the channel is denoted by L effective. So here, if you work on the 180 nanometer technology, that means your channel length is fixed. This is your channel length, 180 nanometer. So what is that? This damage, this length is fixed. This channel length is already fixed. Now, most of the advancement, what is the advancement in the VLSI? Okay, one transistor is the effective channel length is 1 nanometer, and if we go for the lower node like 90 nanometer, so here the dimension is less. Here your channel dimension is less. So that means the total size, total area of your device is less. And now our VLSI industry is moving very fast. This is not on the 90 nanometer. Now 65 nanometer is also there, and 45 nanometer is also there. So here you see the all the times your channel length is less. Okay, now again we see the more advancement in the VLSI. One is the 33 nanometer is also there present time, and 22 nanometer is also there, and now we this times 13 nanometer also there. And if we go for the very advanced node, or we say that is a very present scenario is the 7 nanometer. So in this time, this is a very advanced transistor. Your transistor or your transistor is very advanced now this time, because here the channel size is 7 nanometer. Your L length, L effective, that means this is your device. Suppose that my device is like this, so here the channel length is very less. This is a 7 nanometer. So here the size, if you talk about the area, is very less. So it is better you go for the lower technology node. Because in the case of 180 nanometer, the channel length is more. In case of this size, 180 nanometer, your channel length is more. Your device is means the area is more. But here you see the latest trend.
లేదు ఎందుకు
So
ఏం
in
లేదు
the so if the technology is 7 nanometer, that means your effective length is very less, your channel is less, your channel is very less, of course your area factor is very less. Okay, so that is, you have to observe here in this evolution of the VLSI. All the VLSI devices, or every device has a certain channel length. The channel length is already fixed. So now present time, your transistor, the availability of the transistor is on the 7 nanometer. So that means the transistor is very, very small. So now the one question has come in your mind, how it is possible? One transistor is 22 nanometer and another transistor is 13 nanometer, and now present time 7 nanometer. So what is the concept, how to reduce the channel length, how to reduce the area of the transistor? So that is the very important point. Today we discuss how to reduce the channel, how to reduce the dimension of the transistors. Okay, so this is the advanced transistor. This is a very advanced transistors. And now most of the devices, if you talk about your i7 processor, or you see in your mobile, like a very advanced mobile, that is also use the processor. In every processor, the transistor size is 7 nanometer. It is a very less. Okay, so that is the overview of the reducing the area. Okay, but now here, for the technical point of view, for the engineering point of view, how to reduce the dimension, what is the concept, what is the concept behind that, how to reduce the channel length, or we reduce the dimension. So you just remember in your mind, you have to reduce the dimension in both horizontal and vertical dimension. Okay, so if we talk about the vertical, so your L effective, L, and if we talk about the one more dimension, that is W. Okay, so both is important, both factor you have to reduce, then you have a better result, like your area is very less. Okay, your area is very less. Okay, so now we go for the technology, how to reduce the transistor size. That is a very important point, because everything is based on the transistor size. If your transistor size is less, then you have to fabricate more transistor in a small area. So that is a concept. Today we learn this concept, and uh, if you learn this concept, then you have to reduce your transistors, and you reduce your area also of your chip, whatever your chip. Okay, so now I just one more overview about this. I have written here, the reduction of the size is possible by some factor. You decide how you have to reduce this L, how much you have to reduce this value. So suppose that I reduce this value is 0.2, 0.2. So that is a factor, that is a scaling factor. Okay, so just I written here, this is a scaling factor. So you have to decide first how much factor you have to reduce. Maybe your 0.2, or maybe 0.3, or maybe 0.4, anything is possible. So everything is based on your scaling factor. If your scaling factor, you have to decide first, and then you have to reduce your transistor size, maybe your length, or maybe your W. Okay, so this is a very, very important concept, is required to reduce the transistor size, and it is very helpful to design a high performance chip. Okay, so that is a way. Okay, so now in this slide I just present here, in the year 2000, in the year 1971, your transistor is only 2250. The number of transistors is very less. But now here, if you talk about the Pentium series, maybe your Pentium 2 series, that are come in 1997. In the 1997, the Pentium processor has come in the market, but here you observe number of transistors are very means number of transistors are more. And similarly, if you talk about Pentium 4 processor, the number of transistor is very high. So that is the evolution in terms of transistor, number of transistors. Okay, so I think you have something better picture in your mind. Okay, one thing. Okay, so I think you have a better picture in your mind every times your VLSI circuit is going on the advanced way. So advanced way means your transistor is more. Your transistor is more, but your transistor is moving to day to day. Processors are advanced. Your technology or some device, every time it is very advanced. Okay, so I think you understand this one. So now we discuss how to reduce the transistor size. Okay, so this is the 3D view. This is a 3D view of your MOS transistor. This is your MOS transistor. Okay, so here so many parameters are in your device, not only on W and L. Many other parameters are also involved in the device. So if you reduce the W and L, of course other parameter you have to also change in your device level. So you just see here in this slide, this is the complete structure or the construction part of your MOS transistor. This is a construction part. Why I have to say this is a construction? Construction means your materials, your material informations. What is your oxide layer? Where you are placing the oxide layer? Where you are placing the semiconductor layer? Where is your metal layer? So every informations, every material informations or placing information is available on the device level. So this is your device structure. Okay, so this is your device, not a circuit. Circuit means it is like this. This is your circuit. This is a symbol, only symbol. But if we talk about the device, you have to present all your layers. So that's why this is a structure. This is a construction part. So there is no any issue here. This is the MOS transistor. So in the MOS transistor, the top layer, this layer is a metal. Okay, this layer is a metal, and this layer is oxide. Okay, and this layer is oxide, and this layer is a semiconductor. Okay, maybe N type or P type. So whatever what is my objective? My objective here in this slide, I just showed here. If you reduce the W and L, the other parameter is also affect. Not only because in the MOS transistor there is not W and L two factor. Some other parameter is also there. So that's why we have to discuss uh, all these parameters at the device level. Okay, so just one thing I have discussed here, something in your mind. What are the parameters? Suppose that this is the L, and one more is parameter is W. So what is the L? L is the channel length, and what is the W? That is the width of. And okay, one more parameter is TOX. So what is the TOX? Just to understand, is the oxide thickness. This is a TOX means oxide thickness. So oxide means your oxide layer is SiO2. This is your oxide, and this dimension is present by the TOX. This is your TOX. Okay, so the TOX is the oxide thickness. Okay, so here W L and W and Tux is directly proportional to 1 by K. 1 by K. What is a K? K is your scaling factor. That means your if your scaling factor is 0.2, then your Tux value is, then your suppose that suppose that my K value is 0.2. So in that case, your oxide thickness is 2x divided by 0.2. So this is your thickness. This is your oxide thickness. Okay. So these three parameters are divided by 0.2. This is also divided by 0.2, and this 2x is also divided by 0.2. Okay. So I just again I present to you what is the case here. If you look here in this slide. So in this slide, I just show to you. So in this slide, I just show to you, if suppose that this is your L and this is your W, and one more parameter is 3x. These three parameters are proportional to 1 by K. So what is K? K is your scaling factor. You have to decide what is my how much reduction of your device. Suppose that I have fixed my K value is 0.2. My K value is 0.2. So in that case, my my new Q, my new value, what is the new value? Means something after reduction. Your what is your effect? What is the new value of effective channel length? So that is L dash. So this value is L divided by 0.2. So this is a new value. Okay, and one more. Suppose that my K W value is W by 0.2, and what is my Tux? This is also T divided by 0.2. So this is a way for the reduction of the transistors. Okay, so one thing you have to observe carefully. If you reduce the transistors dimension, suppose that if you reduce the W and L or some other parameter like 2x, then of course your power is also less, because here you have to reduce the area. If you reduce the area, your power consumption of your device is also very less. So we talk about this point also. This is a very important point. If you reduce the area of your device, how much power are reduced at the transistor level? So in the transistor level, how much power is possible? How much power reduction is possible? So that is some numerical, something mathematics part are there, or some modeling part in this reduction. So just to understand, if you reduce these three parameters W, L, Tux, your area is also less. If your area is less, your power consumption is also less. Okay, so we talk about this one also, because this is a very interesting point here, because we are not consider only area, we are also consider the power factor. So the power factor is very important role in the VLSI domain. Okay, so this is a very interesting point. If you reduce your area, your power is also less. But how it is possible? Based on some equation, we have to learn this one also. Okay, so now suppose that I just discuss here how your power is, what is the actual power. So you know the power equation, P is equal to V into I. So I is the current flow from in your device, maybe your ID current, and V is the supply voltage. Okay, so this is a very fundamental equation. P is equal to V into I. Okay, so P is equal to V into I. Okay, so now what I have to convey my message here, my information here. If you reduce the dimension, then of course your power is also less. But how it is possible? what is the concept, and how to say my power is reduced. Okay, so now we discuss this one point. Okay, so you know this formula, P is equal to V into I. So here the current or voltage is also scaled down. The current and voltage is also scaled down. Suppose that my voltage is scaled down by V by K, and here current is also scale by I by K. K is a scaling factor. So now what is the new value? So the new value is V into I divided by K square. Okay, I think you understand this one. P is equal to V into I divided by K square. K is your scaling factor. Okay, so suppose that my power consumption is P dash. In the P dash, that power consumption is after scaling. Okay, after scaling. Okay, so after scaling, your voltage is reduced by V by K, and your current is reduced by I by K. So here the voltage is scaled by V by K and current is scaled by I by K. What is a K? K is a scaling factor. So now after scaling, your power consumption is P is equal to VI divided by K square. So no, not this is P, this is P dash. Okay, after scaling, the power consumption is P dash, and before scaling, your power consumption is P. Okay, before scaling, your power consumption is P, but after scaling, your power consumption is P dash. So here the P dash is VI divided by K square. So now you just to observe here, your P, what is VI? What is VI? VI is equal to P. So now what is the actual formula after some simplification? So this P dash is equal to P by K square. So this is the this is a power consumption after scaling. If your K value is less, if this value, if suppose that this factor is very less, then of course this value is also very less. Okay, so this value is also very less. So that is the power consumption. Your power consumption is less. Based on this formula, based on some analysis, your power consumption is less. So that's why this scaling technology is very, very popular, and it is fairly helpful to reduce the area or to reduce the power consumption. Not only on area, this is also helpful to reduce the power. Okay, because here in VLSI there is some parameters is there. One is a power and another is the area and also speed. So these are the very three important parameters. Okay, so these are the three important parameters we have to observe very carefully in terms of circuit design. If you design some circuit, your three parameters must be less: your power, your area, or your speed. Speed is must be high. Okay, so here the two parameters are fairly good. These two parameters are fairly good in the scaling technique. Okay, so I think you just understand using this scaling technique, you have to not optimize the area, you have to also optimize the power. Your power consumption is also optimized. Okay, so that is the very important or very motivation here. Motivations are involved for the low power circuit design. So that's why every technology, already I discussed 7 nanometer technology is there. In the 7 nanometer technology are also using the concept of a scaling. Okay, so we go for the scaling more deeply because this is very helpful to reduce the power, or we reduce the area. Your area is less, your power consumption is also less. So that means we have to learn or go in the deeply what is the concept of scaling and how it is possible, and what are the concept behind all these scenario. Okay, so now we go for more deeply. Here we observe my power consumption is also less based on some mathematics, based on some analysis. So that two factors are very good if we use this technique. Okay, so just you observe here. um, Actually, here the main thing is that uh, this is the your device. This is your transistors, MOS transistor. I think you know this structure very well. Actually, what I have do what here what I have doing here, all the dimensions are reduced. So that structure is after scaling. So one thing, your oxide thickness is reduced by S. So S is your scaling factor. S is your scaling factor. So your oxide thickness is reduced by S. So you have to observe here your TOX value is TOX divided by S. So S is a scaling factor. Okay, so I think you have to just see in the device, in this device, your oxide thickness value is reduced by S, and similarly the channel length, this is your channel length, is also reduced by a factor S. L by S, and the new value is L by S. The new channel length is L by S. Okay, but one more thing you observe very carefully. If you reduce some dimension, then other parameter is also affect. Your electric field is also affect in the device. Electric field is increase. There is some problem. Something is, if you change the dimension, if your L is changed or your W is changed, then of course the other parameter is also affect. Okay, we discuss also this part, how to compensate the electric field. Suppose that your L is increased, W is increased, your TX is also increased, oxide thickness. Of course, your electric field is increased. Okay, but here there is some technique I will tell you after some times how to control this electric field. Okay, because here if there is a problem in the electron flow. Okay, I will discuss all these things on after sometimes if we go on the more analysis. But why what I have show here, what information I have show here in this slide, if your TX is reduced, if your oxide thickness is reduced, and your effective channel length is also reduced, so in that case the most important point is your doping density on both the side. You see here in this structure, this is a 3D structure. So in this 3D structure, your doping level is more doping is required, both on the source side, this is your source side, and this is your drain side. Okay, so in the source there is a doping, that doping maybe ND, this is multiplied by S. This doping concentration is increased because here the compensation is required. If your electric field is increased, if you increase the W, if you increase the L, and if you increase the oxide thickness of your device, of course your electric field is very high in your device. So how to control your electric field? Because the electric field is very important role. So that means you in the both the side, in the both on source side and on the drain side, your doping concentration is more. So that's why here ND multiply S, and here also on the source side, in the drain side, this value is also ND multiply S. So you have to care about this point if you go further if you go for the scaling technology. Okay, so that fine, there is no issue. This is a device. I have shown the parameters. What are the parameters you have to reduce in the transistor level or in the device level? One parameter is 2x. So one technique is a constant field. Okay, another is a constant voltage. So scaling is categorized into two parts. One is the constant field scaling. Okay. Okay. The second type of scaling is a constant voltage. Okay. So this is the second point. The second point is a constant voltage. So what is the myth? What is the difference between these two type of scaling? So this is the first type. This is the first type. This is the second type. The first type is a constant field scaling, and the second type is a constant voltage scaling. So there is a no problem here. Actually, if you talk about the parameters, suppose that my parameter is W and L. So W and L, and also 2x. This is the oxide thickness. Okay. So of course, if you change the parameters at the device level, suppose that your W is changed, L is changed, 2x is changed. Of course, your electric field has effect. Your electric field has changed. Okay, so electric field is changed. That is a problem. How to control this problem? That is possible is only on the constant field scaling. So in the constant field scaling, your electric field must be constant. Your electric field is not change. So please you care about this point. Care about this point. I just one more time I discuss here. Scaling is two type. One is the constant field, another is a constant voltage. Okay, so in the constant field, your electric field must be constant. Okay, so how it is way? Why field is not constant? That is one issue. So if you change the dimension, if you change the parameters like W, L, and oxide thickness, your electric field may change. So you control this electric field, or you have to means if you have to hold this value. Okay, so that is a very important point. You care about this one. That is only possible by the constant field scaling. So in the constant field scaling, your electric field is constant. It is not change. Also sometimes the constant field scaling is also known as is a full scaling, is also known as a full scaling. So this is a one more name. This is a you say it constant field or constant or full scaling. Both name is same. There is no issue. Okay, so just I given one more overview. First we concentrate on full scaling. What is the concept of full scaling? Okay, so now we move to one by one. Okay, so uh, okay, so now we go for one by one and just discuss all the concept or all the concept behind this constant constant field scaling. Okay, so now we talk about constant field scaling. Okay, so I think it is okay. So so what is a constant field scaling or full scaling? Both name are same. Okay, so it may be constant, both name are same. Okay, so now uh, just you understand here your W and L ratio, your W value and L ratio is reduced. Okay, your W and L ratio is reduced. Okay, so in that way your electric field of your device is increased. Your electric field of the device is increased. Okay, so how to control this electric field, how to constant this electric field? Okay, there is a one solution. If your W and L value is changed or reduced, if W and L value is changed, your electric field is increased. But how to constant this electric field? How to constant this electric field? My requirement is my electric field is not changed, but my W and L value is changed. I think you understand what is my objective, what is the requirement. Your W and L value is reduced, and in this case your electric field is increased. But how to control this electric field? How to constant this electric field? What is the way, what is the solution? How to maintain our electric field? It is not change. If my W and L value is changed but my electric field is not changed, so what is the concept? So you have to just a simple method. Your doping concentration is must be reduced. Okay, I have note down here. If your electric field is constant, your doping concentration is increased. Okay, your doping concentration is increased. So that means in this case your electric field is control. Your electric field is control. So that method or that concept is known as the constant field scaling. Constant field means your electric field is constant in all the times. If you change the parameters in the device level, but your electric field is not changed. But here the problem you have faced, if your WL and your oxide thickness is increased or maybe change, your electric field is changed. So accordingly, the solution is your doping concentration is increased in your device, then your electric field is constant. So this whole concept or whole method is known as the constant field scaling, constant electric field scaling or full scaling. Okay, so this is the way